Welcome to the second lecture in the 7th week of our course Analysis of a Complex Kind. This week, we'll learn about isolated singularities of analytic functions and apply what we learned about the Laurent series to these functions. Let's start with the definition. A point C0 is called an isolated singularity of a function f if f is analytic in a punctured disk centered at C0. So here's point C0. And if you can find a disk centered at C0 such that f is analytic in the whole disk with the exception of C0. If such a disk exists, then C0 is called an isolated singularity of f. Let's look at some examples. The function 1 over z is analytic everywhere except at 0 because we can divide by 0, and therefore this function has an isolated singularity at 0. The function 1 over sine z has isolated singularities whenever we're dividing at 0. So whenever the sine function is 0, and that's at pi, minus pi, 2 pi, minus 2 pi, and so forth. And so this function has lots of isolated singularities. It has one at 0, and I can draw a disk around 0, for example this one, so that 0 is a singularity, but the function is analytic everywhere else in that disk. Or I could draw a disk around 2 pi, and the function is analytic everywhere in that disk except at 2 pi. So this function 1 over sine z has isolated singularities at 0, plus minus pi, plus minus 2 pi, and so forth. For the function square root of z and logarithm of z and functions like that, the situation is a little bit different. Recall that these functions are analytic in the complex plane, with the exception of the negative real axis, which we had to take out in order to make things work. So if I look at the origin, right here, clearly the function is not analytic at the origin, but I still cannot draw a disk around the origin such that everywhere in the disk, with the exception of the origin, the function is analytic, because I'm still having trouble with this portion of the negative real axis that's also sitting in that disk. No matter how small I draw this disk, things aren't going to work out. These functions do not have isolated singularities at the origin. The problem is much bigger at the origin. The function 1 over z minus 2 again has an isolated singularity, and the isolated singularity this time is where the denominator is 0, and that's at z0 equals 2. So now I can draw any disk centered at 2, no matter how large, and the function is going to be analytic in that disk with the exception of 2. Now, if I have a function with an isolated singularity at z0, so f is analytic in an annulus, the inside component is very small, as right to 0, and the outside component is r, then by Laurent's theorem, f must have a Laurent series expansion in that annulus. And the Laurent series expansion we learned about last class is of the form it's an infinite sum. I have coefficients ak, and then power z minus z0 to the k, and the sum goes from negative infinity to positive infinity. And so I have a part of this series that looks just like a Taylor series, only positive powers of z minus z0, but I also have negative powers of z minus z0, and that's called the principal part of this Laurent series. Now, basically, three fundamentally different things can happen that influence how f behaves near z0. And we're going to look at examples first that demonstrate these three fundamentally different things that can happen. So here again, you see the Laurent series expansion of f. Remember that f has an isolated singularity at a point c0, and so we have this disk of radius r such that f is analytic in the punctured disk. Here's some examples. Consider the function f of z is cosine z minus 1 over z squared. Remember that cosine z has a Taylor series expansion 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, and so forth. If I subtract 1 from this function, then this 1 here goes away. And if I divide that by z squared, then I find myself with 1 over z squared times exactly this series expansion I found up here. Now, if I actually bring the z squared inside, then this z squared cancels with that z squared, leaving us with minus 1 over 2 factorial. For the z to the 4th, this becomes a z squared, so I get plus z squared over 4 factorial, and so forth. And I notice there are actually no negative powers of z left. So my Laurent series only has that Taylor series looking part to it. The principal part doesn't even exist in this particular example, even though the function f clearly has an isolated singularity at the origin, because I can't divide by 0. Let's look at another example. The function cosine z over z to the 4th. So again, I have my series for cosine z, and I'm going to divide that by z to the 4th. So I'm going to distribute the z to the 4th into the parentheses, so I find 1 over z to the 4th minus z squared over z to the 4th, so minus 1 over 2 factorial z squared, and then z to the 4th over z to the 4th, those cancel out, so I have a plus 1 over 4 factorial, and so forth. In this example, I have some negative powers of z and then lots of positive powers of z. So this one is clearly a negative power of z, z to the negative 4th. This one is also a negative power of z, but the rest, they're all non-negative powers of z. So I have finally many negative powers of z in this particular example. Let's look at another example. The function cosine of 1 over z. How do I get the Laurent series for that? I start with a Taylor series for cosine, and I replace every occurring z with 1 over z. That definitely gives me a series expansion for cosine of 1 over z, and by the theorem that the Laurent series is unique, it must be the Laurent series of cosine of 1 over z. So all I have to do is look at my series for cosine of z, and simply plug in 1 over z for every z. So I have 1, and then instead of z squared over 2 factorial, I have the 1 over 2 factorial, and the z squared becomes 1 over z squared. And the next term, the z to the 4th, becomes 1 over z to the 4th. And then next, the z to the 6th becomes 1 over z to the 6th. And so here, it looks like the powers of z get more and more negative as I go on. So here, I have infinitely many negative powers of z. So here you see three fundamental differences in the behavior of these three functions at the origin. The first function had no negative powers of z. The second one had finitely many negative powers of z. And the last one had infinitely many negative powers of z. This very much influences how the function behaves near the isolated singularity. And so that's why we use this distinction to classify isolated singularities into three types. Here's the classification. Suppose z0 is an isolated singularity of an analytic function f, and so that means we have a Laurent series expansion in the punctured disk around z0. We say the singularity is removable if all the coefficients belonging to negative powers of z minus z0 are actually equal to 0. So ak is equal to 0 for all k that are less than 0. And those are the k's that give rise to negative powers of z minus z0. We say the isolated singularity is a pole if I have finitely many negative powers of z minus z0. So in other words, there exists a largest negative power, so there exists an n, such that a minus n is non-zero, so that negative power occurs, so I have an a minus n term in my Laurent series expansion, and then, for the powers to the right of that, I have nothing to the left. That's where things stop. So ak is equal to 0 for k less than negative n. The index n is also called the order of the pole. And finally, we say the singularity is essential if we have infinitely many negative powers of z minus z0. So here again, a table that illustrates the definition. We say that z0 is removable if I have no negative powers of z, nothing. It's a pole of order n if the most negative power of z minus z0 is z minus z0 to the minus n. We say it's a simple pole, this is a special case of a pole, if the order of the pole is actually 1. So the term furthest to the left is the a minus 1 term. And the singularity is essential if I have infinitely many terms that have negative powers of z minus z0. Let's study removable singularities in a little bit more detail. So remember, a singularity is called removable if, once I form the Laurent series of the function centered at z0, I actually have no negative powers of z minus z0. So all the ak's are equal to 0 for k less than 0. Here's another example. The function sine z over z. Remember the Taylor series for sine z was z minus z cubed over 3 factorial plus z to the 5th over 5 factorial, and so forth. If I divide that by z, I find myself with z over z, which is 1, minus z squared over 3 factorial plus z to the 4th over 5 factorial, and so forth. Since this is a series expansion of sine z over z, and since the series expansion is unique, this must be the Laurent series of sine z over z centered at the origin. But this Laurent series looks like a Taylor series. It has no negative powers of z in it. A Taylor series is actually analytic within its region of convergence. I can in fact plug in z equals 0 into this series, and when I plug in z equals 0 into this series, all these terms go away. What I'm left with is 1. So if I define f of z to have the value 1 at z0 equals 0, then I have a function that's defined and has a Taylor series in a whole disk, and it becomes therefore analytic. So the function that is defined as sine z over z when z is non-zero and 1 when z is equal to 0, we make that into an analytic function. We have removed the singularity that sine z over z had at the origin. Here's the theorem. Suppose z0 is an isolated singularity of f. Then z0 is removable if and only if f is bounded near z0. We just saw that once we've removed the singularity, we're left with an analytic function. An analytic function is clearly bounded near z0, but the theorem says that this goes both ways. Once you have determined that you have an isolated singularity and the function happens to be bounded nearby, you know automatically it happens to be a removable singularity. Next, let's look at poles. Remember that z0 is a pole of order n of the function f. If the Laurent series of f, that's centered at z0, satisfies that the a minus n term is non-zero, but any other ak's for k less than negative n are equal to 0. Here's another example. Sine z over z to the 5th. Remember that sine z equals z minus z cubed over 3 factorial plus z to the 5th over 5 factorial, and so forth. So if I divide that by z to the 5th, I'm left with 1 over z to the 4th minus 1 over 3 factorial times 1 over z squared plus 1 over 5 factorial, and so forth. And the most negative power of z is 1 over z to the 4th. There's no 1 over z to the 5th or 1 over z to the 6th or anything like that. And so we have a pole of order 4 and 0 for this function. Here's a theorem of how to recognize poles. Suppose z0 is an isolated singularity of a function f. Then z0 is a pole if and only if the absolute value of the function goes to infinity as z approaches z0. We can look at that in our example. Sine z over z to the 5th, we see its Laurent series expansion right here. As z goes to 0, 1 over z to the 4th goes to infinity, and it's the term that dominates the entire series. All these parts here behave nicely as z goes to 0, and these two terms go to infinity, but 1 over z to the 4th goes to infinity much, much faster than 1 over z squared, and so it dominates this series. The 1 over z squared can't make up for what the 1 over z to the 4th does. And so this function goes to infinity as z goes to z0. Again, this goes both ways. If you have a pole, the function goes to infinity, but also if the function goes to infinity as you approach z0, then you must be dealing with a pole. By the way, if f has a pole at z0, then you could look at 1 over f, and then that function will have a removable singularity at z0, and vice versa. Why is that the case? Well, if f has a pole, we know that means that the absolute value of f goes to infinity as z approaches z0. By Riemann's theorem, we learned about removable singularities. If I look at 1 over f of z, because f of z goes to infinity, 1 over f of z must go to 0. That's clearly a bounded function here to 0. In Riemann's theorem, that means I'm dealing with a removable singularity. Finally, let's look at essential singularities. Remember that an essential singularity means that the Laurent series of f has infinitely many negative powers of z minus z0. Here's an example. F of z equals e to the 1 over z. How do I find the Laurent series? We remember the Taylor series for the exponential function. E to the w is equal to 1 plus w squared over 2 factorial plus w cubed over 3 factorial, and this is actually true for any w. So this is the Taylor series centered at 0. If you plug in w equals 1 over z, then we find e to the 1 over z is equal to 1 plus 1 over z. We simply replace every w with a 1 over z. So 1 over 2 factorial z squared, and so forth. And so that's the series that you see right here. Clearly, there are infinitely many negative powers of z in that series. Again, because the Laurent series is unique, and because I just found one series, this must be the Laurent series for e to the 1 over z. So we see that this series has infinitely many negative powers of z, therefore e to the 1 over z has an essential singularity at the origin. Let's look at what happens when z approaches 0. What happens to e to the 1 over z? Let's start with z's approaching the origin along the x-axis. And in fact, why don't we start by approaching from the right? So I'm plugging in positive values of x. What happens to e to the 1 over x? Well, as x goes to 0, 1 over x goes to infinity. Because x was positive, it goes to positive infinity. If I plug in larger and larger exponents into the exponential function simply goes to infinity. So as x goes to 0 from the right, e to the 1 over x goes to infinity. Now let's do the same thing but from the left. Let's still take real values on the real axis, but approach the origin from the left. So here I have x values that are less than 0. This time, because x is negative, 1 over x goes to negative infinity. And therefore, the exponential function of 1 over x goes to 0. Remember, the exponential function looks like this. And so when I plug in very, very small negative numbers, the exponential function is practically equal to 0. Finally, let's plug in values on the imaginary axis. So let's see what happens as I approach the origin on the imaginary axis. So these are points of the form ix. Then f of z is e to the 1 over ix, and e to the 1 over ix is the same as e to the minus I over x. The exponent is purely imaginary, and I know that all of these numbers with purely imaginary exponent, they all lie on the circle of radius 1 centered at the origin. So here, f of z remains bounded. It just bounces around on the circle of radius 1. Does the function f has a limit as z approaches the origin? I have seen sequences for which the function goes to infinity, other sequences for which the function goes to 0, and yet other sequences for which the function bounces around the unit circle. So there's no unified behavior whatsoever, and therefore f does not have a limit as z approaches z0. And that's the typical behavior for an essential singularity. Here's the theorem. Suppose that z0 is an essential singularity of f. Then for every point in the complex plane, there exists a sequence zn converging to the essential singularity such that the function values converge to w0. What does that mean? I'm going to draw two complex planes, one for my z's and one for my f of z's. Pick any point over here in the w plane, any point w0. Here's my essential singularity. The theorem says that you can now find points zn that converge to z0 such that their f values, so their images under f, will converge to w0. And this is possible for any w0 that you choose. In other words, not only does the function f not have a limit as z approaches z0, it's as spread out as it gets. Let's look at an example. Suppose f is the function e to the 1 over z. We know that f has an essential singularity at the origin. Let's pick a point w0. say 1 plus root 3i. Here's again the picture. So by the theorem of quasi-Rorty-Weierstrass stress, there must exist points Zn approaching Z0 somehow, such that their images approach 1 plus root 3i. Let's see if we can find such points. In fact, we can find Zn's such that e to the 1 over Zn, which is f of Zn, not only gets close to 1 plus root 3i, but actually equals 1 plus root 3i. How do we do that? Well, it's pretty simple. The logarithm comes to our help. We simply need that 1 over Zn is a logarithm of 1 plus root 3i. Remember, the logarithm is a multi-valued function. The logarithm of the point z is the natural logarithm of the absolute value of z plus I times an argument of z. Which means for a point z in the complex plane, if we wanted to find its logarithm, we need to find its distance from the origin, that's the absolute value of z, and we need to find an argument. The argument of z is this angle plus a multiple of 2 pi. We also spoke of the principal branch of the logarithm, which we denoted with an uppercase L, which was the natural log of the absolute value of z plus I times uppercase argument of z, and the uppercase argument is a specially chosen argument. It's between negative pi and pi. Just as an example, the logarithm of 2i, so that's the number right here, would be the natural log of the length, so the distance of 2i from the origin, plus I times an argument of 2i. And now we know the distance of 2i from the origin, that's 2, so it's a natural log of 2. And the angle that 2i forms with a positive real axis is a 90-degree angle, so in radians, that is pi over 2. But because we're talking about lowercase argument here, we have to take into consideration all possible arguments, so possibly 2 pi n gets added to that. On the other hand, if we talk about the principal logarithm of 2i, that is equal to ln of 2 plus I pi over 2, because pi over 2 is between negative pi and pi. So now we want to find the logarithm of 1 plus root 3i. So we need to find the distance from the origin, we need to find the length of 1 plus root 3i. But we simply find that by dividing that variant there with the square root of the real part squared plus the imaginary part squared. And so that's the square root of 1 plus 3, which is the square root of 4, and that's 2. We also need to find the angle, but this is a special triangle that we're talking about. This length here is 1, this length is 2, and this length is root 3. This is one of the special triangles. This is a triangle where this angle actually is a 60-degree angle, and that's pi over 3. So we know the argument of 1 plus root 3i is equal to pi over 3 plus 2 pi n. So now we know what the logarithm is. We know that the logarithm of 1 plus root 3i is the natural logarithm of the length, so the natural logarithm of 2, plus I times the argument. And that's what you see right here. So we want 1 over Zn to equal this number, so therefore Zn needs to be the reciprocal of this number. So let's take that as our Zn. What happens to Zn as n goes to infinity? Well, as n goes to infinity, the denominator gets larger and larger, so Zn itself goes to 0. So indeed, we just found points, Zn, that go to 0 as n goes to infinity. We're hoping that f of these points will approach our special point w0, which we chose to be 1 plus root 3i. Let's check it. E to the 1 over Zn is simply e to the natural log of 2 plus I pi over 3 plus 2 n pi I. How do we compute that? We can pull this apart. E to the ln of 2, e and ln cancel each other out, that's simply 2. E to the I pi over 3 is the next, and e to the 2 n pi I is equal to 1. Remember, if we have a sum in the exponent, that becomes a multiplication once we pull the exponential function apart at the exponent. And what is e to the I pi over 3? E to the I pi over 3 is very similar to the example that we just looked at. Pi over 3 is that 60-degree angle, and it's simply the number that we looked at earlier, but scaled down to have length 1. So we had looked at this number up here, 1 plus root 3i, and now this number gets scaled down to length 1, so the number now is 1/2 plus I times root 3 over 2. We multiply that by this 2 right here, and we're back to our number w of 0. So e to the 1 over Zn is indeed w of 0. Not only did we find Zn's approaching our essential singularity Z0, such that the f of Zn's converge to w0, but more is true. Our f of Zn's are all equal to w0. So we showed something that is even stronger than what quasi-Rorty-Weierstrass wanted. We observed a much stronger result that is also true, but it's much harder to prove for essential singularities, which is Picard's theorem. Suppose that Z0 is an essential singularity of f. Then for every w0 in the complex plane, with at most one exception, you can find those sequences that we just found. The sequence Cn converging to the essential singularity such that f of Cn is equal to w0 for all n. Here's the situation. We have our essential singularity, and for any point w0 with at most one exception, so there's one point that might not work. But for any other w0 in the complex plane, you can find a sequence of points Zn converging to Z0 such that f of Zn is equal to w0 for all n. So they land right on top of w0 for all n. Let's finish with an example. The function e to the 1 over z has an essential singularity at 0, and we already saw a sequence Zn such that f of Zn is equal to 1 plus root 3i. And you could see that we could have done the same kind of construction for any other point, with one exception. E to the 1 over z is never going to be equal to 0 because the exponential function does not take the value 0. So for 0, that wouldn't have worked. w0 equals 0 is the one exception in Picard's theorem, but for any other w0, you could have done the same construction that we just did and found a sequence Zn converging to 0 such that the f of Zn is equal to the chosen point. For example, take w0 equals 1. So we want z's such that f of z is equal to 1. We want e to the 1 over z to be 1. How can we make e to the 1 over z be equal to 1? Well, that means 1 over z needs to be of the form 2 n pi I, and so therefore zn could be chosen as 1 over 2 n pi I. Those zn's clearly go to 0 as n goes to infinity, and f of zn is 1 for all n. In the next lecture, we'll start learning about the residue theorem and how it relates to functions with isolated singularities.